Hi, I'm Frank Lamb with Automation Consulting, and this is a webinar from August 21st, 2020. Okay, I'm going to go ahead and start this webinar now. This is the program that we worked on last week, and as you can see, I've added a number of function blocks and function calls. Go over a little bit about what we did last week. This project is named PRJ1 August 2020. And last week, of course, we created OB1, some other OBs here. OB1 itself contains some simple logic, creating always on and always off bits. We did a cycle counter here. If I bring up the VAT table for this, you can see the various VAT tables that we have here. I named this one junk. And this counts the cyclic scans. You can see it's counting pretty fast here. Every time it goes through OB1, which calls all the other routines, it adds one to a register. And the logic for that is right here in statement list. So I load one, then I load memory word 102, add the 1 to it. That's what the plus I is here, and I transfer it back into itself. So this is pretty typical logic. It's very similar to a counter. There are various subroutine calls here. Last week we also created this control system function, and the control system function has most of your typical system functions in it, like auto mode, manual mode, auto cycle. We'll take a quick look at that. So this is very simple logic again. When I press the auto push button, it sets auto mode. If I press the manual push button, it sets manual mode, resets auto mode. Cycle start, you must be in auto mode. I press the cycle start push button, and provided I am allowed, we'll go ahead and go online here and take a look at it. Provided my cycle start permissive is allowing me to go into cycle start, then I run a 3-second timer. Typically here you would sound a horn, something like that. Do a quick overview of what the actual PLC I'm using here is. So I build trainers, much like this one shown here. And this trainer happens to be an Allen Bradley, but it does show some of the features, stack lights, things like that. Hello, Atif, how are you doing? Can you see the camera that I'm showing here? It's interesting because I can't see it. There we go. Now I can see it. I'm going to go ahead and put it in here. So the actual trainer that I'm using right now is this one. It's a S7 315, and it is similar to this trainer right here, which is an Allen Bradley trainer, has different buttons and things like that. And I simulate all the auto mode on this because I don't have all these buttons wired in here. But that's the general idea behind what I'm doing here. Okay, so I'm going to get back to where I was. This auto sequence here, or this system routine, actually, this control system routine, if I press this cycle start push button and the permissive is allowed, I will go into auto cycle. You can see I'm already in auto cycle here. And the way that I actually run this is by using the VAT table. So this is my This is a junk vat table. It's just sitting here looking at all the counters. It has a variety of things in it. Let's see my other vats. We're going to use this one a little later. And I'm going to open the system variable table here. So the system variable table has all these push buttons and things in it. Cycle start, push button, auto, manual, that sort of thing. So here you can see I'm in auto mode. I'm in auto cycle. If I want to stop auto cycle, I can simply press this button, and I'm just going to toggle it here since I don't have real push buttons. And you can see when I toggle it, my light starts flashing down here. This is the stack light, so I made little imitation stack lights. Again, similar to this. So you can see this light here, if I hit, let's see, cycle stop, there we go. So you can see cycle stop here makes the light blink, just like you see here on this screen. The logic for that looks like, make sure we get the camera back here. The logic for this looks like this. Right, so the timer runs, I latch in auto cycle. What's actually making this blink is if I go here into the outputs routine, I have a little clock. And you can see if I'm in auto cycle, it doesn't blink. If I'm not in auto cycle, I use this little 500 millisecond pulse. This pulse comes from the hardware setup. So if I go in here to the Somatic Manager and look at my hardware, this is a 315. And right here in this processor, I can assign the clock memory byte, right? So I've assigned memory byte 1, which is M1.0 through M1.7. Right, so we can close this. And what that looks like is if I go to another variable table here, lots of windows in Siemens, right? So another variable table that I have down here is this clock variable table. And if I look at it live, you can see things ticking along here. And that's because I assigned that memory byte 1, right? So as soon as you do this, you can also go in and name all the bits if you want to. And they blink at different rates. So I name them millisecond 100, millisecond 200. So these are convenient bits to just blink things. And that's how I blink the auto sequence or the auto cycle light. So that's what I'm doing there. So if I go down here back to the system routine, you can see it down here blinking. I'm going to go ahead and do a cycle start now. So a lot of these bits are just bits in that routine. I'm going to go ahead and turn this on. It goes tick, 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 and eventually latches in. And we are now in cycle start. So we'll turn the button back off. And the logic for that again was here in this control system. So you see the timer expired, 3-second timer, and I latched in auto cycle. If I wanted to stop my auto cycle, if I'm in auto cycle and I press the cycle stop push button, I get a cycle stop request. And if my cycle stop permissive is on, which says maybe my pick and place isn't moving apart or something like that, then I would have a permissive and I would say, okay, it's okay to stop auto cycle. You don't want to just stop auto cycle anytime, right? You want to stop it at a time that's convenient for you. That's a lot of times why people get locked up in sequences, right? You hit the E-stop or something, the sequence doesn't finish, and you're stuck with a part in your gripper or something like that, and you can't get out of it. Okay, so that's why we wait for the cycle to finish and get a cycle stop permissive here. Okay, a couple other things that I did here. I did add a variety of OBs. So these OBs all have different purposes, and I'm going to go ahead and display some of the different kinds of OBs there are. I had one of these prepared here. We'll go ahead and bring it up. There we go. So these are some of the OBs and what they do. So we've been doing things from OB1. OB1 is the cyclic routine. It runs all the time as fast as it can, right? Constantly scanning. That's the one that we were looking at, the counter just constantly running up. So where I was doing the load one and add to a register, you can see it counting up here in the cyclic routine. You also have OB 10 through 17. Those are time of day interrupts. They would happen whatever time you set in your hardware. If you set it at noon, then you will have a one-time run of OB 10 at noon, right? And then maybe I set OB 11 at 8 o'clock p.m. and it would run one time at 8 o'clock p.m. So what these are useful for is logging events and things like that, like shift changes or something like that. Time delay interrupts, much the same thing, but they happen after a certain period of time, and you would set that time again in hardware. These are cyclic interrupts. I'm actually using OB35 here. OB35 is set to 100 milliseconds. So if I go in and look at OB35, we'll look at the code that I put in there. Again, I put some statement list. I load one. I load a memory word register and add it, right? Plus I, integer add, and transfer it back into itself. So I'm adding to myself there. And if I go look at my junk table, I can see it ticking along here, right? It's doing it, looks like it's doing it once every second. So I run this for a 1 second cycle time, 1,000 milliseconds. This one you can see is counting much faster. It just keeps adding every time I do a scan. And this one first scans. Go back and let's see, look at, I got to find my windows open here. That's always one of the problems. There we go. And here's my pictures. There we go. So this was the OB list, and this was processor startup. So OB 100 here is periodic scans, and I do the same thing inside of that. Actually not periodic scans, first scans. So I've had 11 restarts. That's what this does. It runs one time every time you restart the processor. These OBs are very useful. OB121, you don't even have to put any code in it, but what it does is it runs if you have a programming error, and it immediately goes to OB121 and does whatever you tell it to do. If you don't have any code in there, it still stops you from going out of run mode. That's its job, right? So for instance, let's say I forgot to download a function. I forgot to put FC5 in there, but I accidentally called FC5. This will prevent you from actually stopping the processor. It will continue to run. You will have a system fault, but it will, again, allow you to keep running. And I put these, OB121 and 122, in every program that I do. Very, very important OBs there. The other ones I put in every program I do are OB82 and OB86. What these do is, again, prevent you from going into stop mode if you lose something like a Profinet or Profibus node. So that's its job. All OBs is blocks with a special purpose of some kind. You know, it runs all the time, or it runs only on startup, or it runs if I have a failure of some kind. That's what all these OBs do. So all this is available, of course, on Siemens website. The next thing that I'm going to go through here, and this is a kind of a complex thing, and this is what I had on my list today to cover is we're going to do a little statement list. And this is a recipe selection exercise. So imagine that I have a bunch of parameters set and I need to select a recipe. I need to move a group of parameters into some registers and then use those parameters to run something, right? So maybe it'll have times or weights or whatever in it. So for this particular exercise, the first thing I did was created a UDT. If there's a question as to what a UDT is, do you understand what that is? That's a user-defined data type. Have you heard of those? This particular UDT looks like this. So what I did here for the recipe is I created a single recipe, and it has a couple time set points in it, a delay time and a dwell time. It has an integer here called stage number, and all I did with that is I put the recipe number in it, but it could be anything you want to put in there. I also put some temperature set points in there, a delay temperature and a dwell temperature, and I'll kind of show you what I did with that later. And then I put an array of valve configurations, and I put numbers in those arrays. That's the general idea for this. So the UDT is a structure. It does not go into the PLC at all. It exists only on your laptop, right? So when you create it, it stays right here, right? So it doesn't get downloaded or anything like that. What you do with the UDTs is you use them to create other things. So for instance, last week I did a runtime UDT. It had hours, minutes, seconds, things like that. And I used the runtime UDT to create some of these data blocks like auto time. Okay, so recipes, I used that recipe UDT and I created this block, which is the recipes data block. Okay, so if I look at this in declaration view, you can see there's the UDT. So I said the current recipe is of data type UDT recipe, right? So UDT2 is that. So if I open this up, you can see it takes 38 bytes of data and it's right there. I also have a number in here, and that is the recipe that you're going to select. And I purposely made this difficult. There are easier ways to do this. I could have created, you know, say 7 data blocks, each with their own recipe. Could have created a whole data block with a current recipe and just copied it. But I wanted to use these pointers in here to jump around inside of this data block. So I'm going to do a data view here, and you can see when it expands out, it looks like this. It's a big data block. So current recipe, there's all the elements we put in the UDT, right? Delay time, stage number, temperature, high, low, all these different things. And you can see they actually have numbers in there. Right now they're displayed in hex, but I can use the variable table to display them however I want to. There's recipe 1, recipe 2, recipe 3, and so on. And that's because I created an array, right? So view it back in declaration view. I created an array from 1 to 10 of data type recipe. That's why I have recipes 1, recipes 2, and so on. So again, we'll go back into data view. You can see pretty long data block. Goes all the way down to byte 418. So the idea is we want to take some code, and I want to, for instance, grab all of recipe number 3, right, which starts at 116 and ends at 152, and I want to put it here in current recipe. That's what I want this code to do. And then I would take current recipe and I would run it, right? And I actually have a little process routine where I use some of the data out of this, the temperatures and the times, and actually run a little process. So now let's take a look at the code And I do have the code open here somewhere. We'll close some of these other ones. This gets obviously a lot of traffic here. We probably don't need this one anymore. We really don't need this one anymore. A lot of people like to maximize these. The problem with maximizing them is you can't see all of the routines behind it, right? Process, this is the routine that I actually run this recipe in, and I'll go through that a little bit later here. And I do run a simulation. We'll use that a little later. Well, yes, sure, we'll go ahead and save it. Process one, we'll leave that open. And I'll go ahead and open the code now, which is again in the manager. And process one, recipe select. This is the code. Now, one of the things about Siemens step 7, you cannot do this in ladder. You must do it in statement list. It's kind of complicated and messy. A lot of people don't like statement list, but that's the nature of Siemens. I did document a lot of this. So we're going to be using something here called the any pointer. And the any pointer is right here. I created a value, right, of data type any, and I just named it PTR. So that is a local variable. And this is where you put all your local variables. We covered that last week. And I'm going to show you what the pointers look like. So we're going to open a few different little pictures here. There's one. This is the structure of the any pointer, right? It has a lot of different things in it. I'm going to open, let's see, memory area coding. Here's an example of some of the pointers. So this is what you can do with pointers. I can type in p-pound and I can address something, a byte and a bit of anything, like a data block or an input area or an M area or a DB or anything. That's the idea behind these pointers. I point to different areas within these data blocks. This one is the most complicated, right? It points out the area of the data block, the byte number, the bit number, the length, and the type that it is. So if I type in p-pound db42.dbx2.0, and you must specify this to the bit level, and I say byte 12, I will get 12 bytes starting at dbw 2.0, right? So that's the idea behind this. So if I grab that data block that I was showing you before, I can grab any section, right, and then move it, use a block move instruction, and take this section and move the data inside of it to this section. That's the idea behind that. We'll take a look at what some of the different elements of this mean. So here's the pointer again. Have I lost my pointer? Nope, there it is. So this is the pointer we're constructing. The area that I put in here is going to be some kind of a hex code, right? So I would have D#16 means that I'm in hex, and then I would put the code of 80 if I wanted to use an IO area. If I wanted to use a DB, I would put the code 84. Right, that's what this means. It means put the hex code 84 in here if you're wanting to move something within a data block. If you're wanting to move something in the local stack, then you would move an 86 in there. If you want to move an input pointer, then you would put an 81 in there. That's what the coding is for that. So that's memory area coding. Let's see, data type coding. I'll show you that. It's much the same kind of thing. If I want to move double words, then I would move the number 6, right, within this pointer area. take a look at what the structure of the pointer looks like. And so it's 10 bytes of information, and it looks like this. So what I have to build here is a structure that has this 10 hex. That's what this means. If I'm doing step 7, then I want to put a 10 hex in byte 0. I want to put a whatever the data type is in byte 1. So when I talked about the data type, that's this. I want to put, if I want to move bytes, then I would put a 2 in byte 1. Right? The repetition factor is how many bytes or how much data do I want to move. I want to put that in byte 2 and 3. So byte 2 and 3 allows you 16 bits. That'll let you put all the way up to 65,000 something bytes, right? Data block. If I put a 0 in there, then it's not a data block at all. I didn't put that data type in there, right? And then the byte address, etc. So what we have to do is build this pointer literally byte by byte. And that's what this code does. Okay, so I'm going to go ahead and go back to where the code is and show you exactly how that was constructed. And here is the code. So the first thing we do is we load the address register. So if I go online here and look at it, my address register is typically over here. I can build this literally byte by byte. So that's what I'm doing here. And I have kind of documented what each step does. So we'll go ahead and go offline, look at the comments also. There we go. So I load the starting address of this any pointer that I created up here. That's what this is. Then I have to load the syntax ID of 10 for step 7. So that was this thing I showed you before that said step 7. Where is it? I've lost it again. So hard to get at my taskbar with all this open. There we go. Look at all my pictures, and this is it. So I need to move it to the other screen where you can see it. So that's what this says. It says put 10 hex in here, and then put my data type in here. So that's what this code is doing. Right, load the pointer, put the 10 hex in there, put my data type of byte, which is a 2. So B pound 16 pound 2, that is a hex 2, and take that and put it into byte 1. So that's what I'm doing. I'm loading the data and I'm moving it into the local byte 0, 1, 2, local word 4, local word 6, etc. And I'm building this structure one element at a time. This is the only way, unfortunately, to do this in step 7. Now, if you're familiar with Allen Bradley allows you to do this within an array. You can simply put a square bracket and then put a number in the square bracket, and it will move whatever you pick up as an array element. I can move a whole UDT. TI Portal in Siemens does the exact same thing. I can use an array and simply put the pointer in the square brackets. I don't have to build this kind of code. But in step 7, this is pretty much your only option for building this structure. I load a 38. That is the repetition factor. That's the size of the recipe. Remember, the data block that we built in here was 38 bytes long. That's what this is. So 0 through 37 moves all these valve configurations, things like that. Okay, then I load 50. 50 is the data block number. So this was DB50. You can see it right up here, right? Recipes. So load data block 50. Load word 84. Once again, we're loading into, I think, byte 7 there, and 84 is, let's see if I can find it. Data type coding. There we go. It's not 84. So this is the data type coding, the memory area coding. That's this one. Here's our 84, right? So you have to have all this. This is saying it's a data block. So by putting an 84 in there, it says a data block is what I want to move data within. So again, building that. Then I load recipes, the selected value, and I load a 38 for which byte I want to move, and I multiply it. So this is the thing that gives me an index that points down here and jumps to location number 38 right here. So that's selected. Okay, then I load 40. That is the offset. I add it. So the reason I'm doing that is here's your 40. So I'm saying go to 40 and then multiply whatever my selected number is. So if I have a, let's say I have a 2 in here, I would have 40 plus 2 times 38, right? And I would end up down here, 2 times 38, and I would get my third recipe. So at this entire code is simply building the pointer, this pointer right here. So this is how complicated, right, it can get to build this stuff. Let's see if I can find my structure again. So we built this. This is what we built here. The reason that we did the shift left word, you can see it down there at the bottom. It said shift left word 3. That made this space, right? This put the bit address in there. So that was the reason we did the shift left word. So at that point, you've built this pointer. Then you have to use the pointer down here, and you call a block move. So when you do this, block move is one of Siemens built-in functions, right? It's a system function call rather than a regular function call. Your source block is pointer. So this is the pointer that you just built in the previous logic. Okay, return value, you just have to have something in there. So I put memory word 500 in there. This usually, what this does is returns an error. That's the purpose of the return values. Destination block is recipes, current recipe, right? So p-pound db50.dbx0.0 is a pointer to that recipe's current recipe structure inside of recipes. So messy, complicated, I agree, but that's what we're doing. We're pointing to this offset and we're moving it into here. Okay, so let's see how it works. Let's take a look at the VAT tables for it. I have a variety of VAT tables open. Go ahead and open up current recipe. So the current recipe right now has too many things open here. So I'm going to go ahead and close this one. Do I want to save it? Sure. So if you monitor too many things at once, like this, you will say you can't see all these numbers, right? I can't look at everything at once. We'll go ahead and save that. There we go. So you can see all these values in here. Current recipe, delay time, etc. I put a 3 in here. If I put a different number in here, what I'm going to do is move, and I'll bring up close this. Do I want to save it? Sure. Bring up a different VAT table that I created for all the recipes. So what this did is allowed me to put numbers into all the individual recipes. This takes quite a while, right, to build this variable table. You had to put all these in here, DB50, DBW40 through 78, 38 bytes with all this information in it. So what you can see here is I put different numbers in every recipe. The recipe we were looking at before was the third recipe, which is actually recipe number 2. So that's recipes 1, recipe 2. So I actually took this one and stuck it into here. Right, so if I change this number, we'll put a 1 in here and load it in, and you'll see these numbers change. So shotgun it in there, bang. So now I've got 3 seconds here, I've got 8 seconds here, and I got this stage number in here. So what the stage number actually is the recipe number, right? So I put stage number, it was just so I could keep track of things. So I put stage number 1, stage number 2, stage number 3, right? I just put those in there and then kind of put random numbers into the different locations. So that's the idea behind all of these data moves, right? I'm taking one of the selected recipes and I'm moving it into the current recipe, which is this. And you may have something like this where you work, a recipe is not necessarily a recipe like you're baking a cake, right? It is just a collection of parameters. So valve configurations, for instance, if I look at this in binary, I can see a pattern, right? And I could move that pattern into a valve bank and turn those valves on. So that would be a typical thing to do with these recipes, move the valve configurations into something. Okay, so what did I do with this current recipe? I actually ran a little process, kind of an imaginary process, and it is in here in process 1. So we're back to ladder here. Ladder's a little more fun, a little easier to read personally for me. If I'm in auto cycle and my process is in step 0 and I say run process, then I will move a 10, right? Then I go down to the next section. If I'm in auto cycle and I'm in step 10 in this sequence and my temperature is in range, then I run a timer. The timer's set point is that delay time that we did up here, right? This delay time. So there's my 2.5 seconds. It should run 2.5 seconds after its temperature in range. Once the timer is expired, I move a 20 and I'm now in the 3rd step. So here's step 20. If I'm in 20 and the temperature is in range, the next in range, then I run another timer, and this is the dwell timer. So you can see I have delay time and I have dwell time. I'm running 2 different timers. Once the dwell timer is done, then I move a 30 in there. And in step 30, all I do here is run a fixed time period of 1 second. So you can actually see this. If I go look at it, you can see I'm in, right now I'm in step 0. I can actually run this. The reason I can run this is because I do some simulation. The simulation routine kind of feeds back things like this temperature in range, right? If I would have just run the timers, it would have simply run a 2.5 second timer and then a 7.5 second timer. But I also put some temperature set points in here. So what do my set points look like? Again, look at the bat tables, current recipe. I've got 385 for my delay temperature. I've got 412 for my dwell temperature. And I'm actually going to ramp up to those as shown in this diagram. I'll bring it over. Whoop, wrong thing. I opened my drawing instead of my graph. We'll open the graph instead. There we go. Well, while that's opening, I'm just going to close it. But what it looks like is this. So in step 10, and there's Corel Draw, we'll close that. There are two things with the same name in there. So there we go. So this is what I'm doing in this process. I start here at something like room temperature. And again, these are all fake temperatures. I'm simulating these, and I'm going to show you how I simulate them. But in step 10, I'm going to ramp this temperature up until I hit whatever my set point is. So you can see my first set point was 385. I'm going to ramp up until I hit that set point, and then I'm going to run the delay time. Right, current recipe delay time looks like 3 seconds. Actually, I don't know if that's live. Let's see. Yeah, it is. Right, 3 seconds. So that's what's currently in here. So I'm going to run 3 seconds here for my delay time. Then I'm going to go into step 20. Again, I'm going to ramp up to the next temperature, and I'm going to stay there for my dwell time. Then I enter step 30. I stay there for 1 second, and I reset my temperature. Let's look at the simulation and see how I did that. The simulation itself, I'm faking all of these temperatures. And the way I did that is when I click on the run process, I say, okay, there's a part at the oven. So this is an imaginary part, and I just click the bit, and there it is. Let's see, okay, there we go. So if I turn this on, I use a one shot, and I say there's a part at the oven. The reason I used a one shot here, by the way, is so that if I accidentally leave this on, I can turn it off down here at the end. That's what one shots do for you. So when I get to step 30, I say reset the part at the oven. It's no longer there, right? So I make it disappear. Okay, so that's this logic. A little bit of ladder there. I set the part at the oven. If there is a part at the oven, I again use a one shot, and I move what we consider in the US room temperature, which is 75 degrees. Now, I realize most of you guys are from other countries and you use Celsius, and Celsius room temperature is maybe 20 degrees, right? But I used all Fahrenheit here. So 75, and I put that into the part temperature. And this is just a simulated part temperature. Then I ramp the temperature. I say, again, if there is a part at the oven, which I latched up here, and I'm in step 10, then I use that same clock pulse that I was talking about. You see it flickering there. That pulse is flickering very fast. It's doing a 100 millisecond pulse. Again, with a one shot. You wouldn't want to do this without the one shot, because what it would do is continuously add every scan while this was on. I just want to add one time every 100 millisecond pulse, right? And so what I do here is I take whatever the current part temperature is, and actually, let's look here. Here's where I do my add. I take the part temperature and I add 1.1 degrees every time I get one of those pulses until my temperature reaches my set point. So that's what this is. If my part temperature is less than or equal to my set point temperature, then I add to it. And what'll happen is eventually I'll hit that ramp that we looked at here. Let's see if this works. Yeah, there we go. I'll hit this and I'll stop ramping up, right? So during that delay time, I hit that point and I just stay right there at that set point. Then I go into step 20 and I do the same thing. So step 20, go down here. In step 20, add, right, 1.1. I could have added anything. If I wanted to, I could have ramped up even faster here and added to the part temperature. And then at the end of the temperature, I go ahead and reset the part at oven bit. Okay, so let's go ahead and watch this run, see how it operates. There's the current recipe, and once again, made a VAT table. If I had, real push buttons and a graphing software and that kind of thing, it would be even more realistic. But let's see, process 1 simulation right here. So again, we'll try to look at it. It may kick me off. There we go. Process step 0. You can see it going through the processes, and you can see the part temperature. Right now, part temperature is at 400. If I toggle this bit, this is the run process bit. Turn it on, turn it off, and you can see it's ramping up. So it's doing this. It's ramping up to my delay time. Okay, you'll see it hit the delay time. It was 385 degrees, I believe. So it keeps ramping up. I'm still right in here. And it stops, right? So I'm delaying here, and I had a very short delay, and then I ramped up to 412 degrees. That's a 7.5 second delay, I believe, or 8 seconds. I kick to 30, and then 1 second later, I go back down. So all this is just simulation, right? Simulating the ramping up of a temperature like shown in this graph. It took a lot to do that, right? I had to select the recipe number, which changed those process set points that we had in here, right? I had to fill all these values. I did that yesterday. The good thing is I'll be able to reuse this. I'm going to reuse this for some other training videos that I'm recording. And of course, I will put this online. I'll put this on YouTube so that people can watch it. But any questions, Atif? Do you understand pretty well what's going on here? Let me see. There we go. I think you're muted. Unmute audio. There we go. Huh. Okay. I guess you can hear me. I can't see you. There we go. Well, it unmuted. See, this is what I see. So I could hear you before, but for whatever reason, I can't hear you now. So you may have gone on a break or something. But anyway, that's what this is doing, right? Going through all those steps, process steps. We'll run it one more time here. Just toggle this. See it ramping up. Here we are at a delay time, and we're ramping up to the dwell time. Okay, so we'll go ahead and put a different recipe in here now. After this is done, we reset to 0. Now I'm going to do a recipe select again. So we'll set it. We'll see what kind of set points we have here. Pick something with a little bit longer set point. This is 3 seconds and 8 seconds. This one's 2 seconds and 5 seconds. 3 and 8 again. Four and 11. We'll do that. So this is the 4th recipe, even though it says recipe 3. So I'm going to put a let's see, actually 1, 2, 3. This is the third recipe, so I'm going to put a 2 in here. And we should get, if I put a 2 in here, I should get delay times of 4 and 11 seconds. Shotgun it in there. Okay, I actually need to put a 2 in here to get my 4 and 11 seconds. There we go, 4 and 11.5 seconds. And our temperature set points are 294 and 354. So we'll go ahead and run it, make sure that it's doing the right thing. So this time it should ramp up to a lower temperature and stay there longer. Okay, so we're at 295 degrees. Then we're going to ramp up to 3 something. There we go, 355-ish, 354. We're going to stay there for 11 seconds. And we're all done. So that was pretty much it as far as today's webinar. We covered some complicated stuff. Pointers. Of course, pointers are messy. I'll go ahead and put those back up there in case anybody wants to copy the screen. Bring the manager up. And again, that's the code. And the idea was to build this pointer, which looked like this. So if anybody needs to type that in, of course, you can just pause the video and go back and copy that. Do a screen capture, whatever you want to do. But this is the core of what we did today. Once again, it had to be done in statement list. You can't do this in ladder in step 7. It's an old software package. Well, thanks for attending, Atif. Atif was the only person that I could see attending, but I know last week I only showed one person, Lloyd, and there were actually other people on the call. I just didn't notice them. But anyway, that is the end of this, and thank you very much.